Hi everybody, let's do IXL 8th grade F12. These rules over here should be the only rules that we need for this. So when we're multiplying, we add the exponents. When we're dividing, we subtract the exponents. If we're raising a power to a power, we multiply the exponents. If we have some base to the 0th power, then that's just equal to 1. And if we have a negative exponent like a to the negative b, that's the same thing as 1 over a to the b. Okay, so let's get started. Over here we're dividing, so we're going to use this rule. If I'm dividing, then I know that I should subtract the exponents. So 3 to the 8th divided by 3 to the 4th is, the way to do that is just 3 to the 8 minus 4. Okay, 8 minus 4 is 4, so we get 3 to the 4th power. Okay, which just means 3 times 3 times 3 times 3. I'm using the dot over here to mean multiplication. Sometimes people use an X for multiplication, like I wrote over here. Sometimes people use a dot for multiplication. So I'm just using a dot here. So this is going to give me 81, because I know 3 times 3 is 9. 3 times 3 is 9 again, so I have 9 times 9, so that's 81. Okay, and some of these rules are actually easy to remember where they come from. So another way that I could have gotten that is to say 3 to the 8th means 3 times 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 3. Okay, so 8 times over 3 to the 4th means 3 times 3 times 3 times 3. So this 3 is just going to cancel. So we have a lot of canceling going on here. And then what's left is just these 4 3's being multiplied together, which is the same thing that we got over here. So it's not too hard to see where this rule comes from. Just to remind yourself, if it just comes from the fact that these numbers are canceling out. So if we had 8 in the numerator to begin with and we had 4 in the denominator, then there are going to be 4 left over, because 8 minus these 4 that canceled out leaves us with 4. Okay, so anyway, we're going to put 81 in here. All right, 4 to the second times 4 to the second. So we're multiplying here. We can use this rule that says if we're multiplying, we need to add the exponents. So to do this, we could do 4 to the 2 plus 2 power, because this is 2, and then I have another 2 over here, which is 4 to the 4th. Okay, right? 2 plus 2 is 4. And that just means 4 times 4 times 4 times 4. All right, so let's see if we can do some quick mental math. This one's going to be a little bit harder, but 4 times 4 is 16, and then I have another 4 times 4 here. So I have 16 times 16. Okay, well, and for this, you could do that in a calculator. I wouldn't mind. But anyway, that's 36, and then that's 6 times 1 is 6, plus 3 is 9. And 1 times 6 is 6, 1 times 1 is 1. Okay, so we're going to get over here 256. Oh yeah, that's right. No, I should have known that. All right, but again, it's not too hard to see where this multiplication rule comes from, because 4 to the second power just means 4 times 4, right? 4 to the second power means 4 times 4. Then I have another times over here, another multiplication symbol, and then 4. I have 4 to the second power again, so that's another 4 times 4. Okay, so I have 2 4's for this one. I have another 2 4's for this one. So altogether, I have 4 4's, right? 2 plus 2 gives me 4. So I have 4 4's altogether, right? So if we're multiplying, then we would just add the exponents. That tells us how many of the number we have all together. If we have B over here and we have C over here, then all together we have B plus C. Okay, so anyway, the answer for that one is 256. Okay, 10 to the 9th divided by 10 to the 7th. Again, if I were to do 10 times 10 times 10 times 10, blah, 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 9 times in the numerator, and then 7 times in the denominator, then 7 of those 10s would cancel out, and there would just be 2 10s left over, right? Just like we did. Rewind for a few minutes, and that should make sense. But anyway, I'm just going to use the rule over here, which says if I'm dividing, I'd subtract the exponents. So 9 minus 7 is 2, right? So I have 10 to the second power, which just means 10 times 10, and that's 100. Okay, so over here we're multiplying. We're going to use the multiplication rule. We're going to add the exponents. So the base is 2. Then we have, again, like we did in the other one, 2 plus 2, because both of these exponents are 2. So we have 2 to the 4th power, which means 2 times 2 times 2 times 2. Okay, and let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16. Can you give me any negatives or anything? Okay, so over here, so how does it want me to evaluate them? All right, so actually this is, for this one, we're not using any of these rules. Why not? Because the bases are different here. So if for all of these rules that I wrote, the multiplication, division, power, 0, and negative, well, at least for the first 3, the bases are the same, right? A, okay? Oh, actually just for the first 2, right? The bases are the same. I have A here and A here, A here and A here. This one, for this one, I cannot use the division rule because I have a 9 here and an 11 here. So the bases are different. So in this case, is there any way for me to simplify this? I don't think so. 9 and 11 don't have any common factors. So we'll just do 9 to the second power is 9 times 9, right? So that's 81. 11 to the second power means 11 times 11. That's 121. I don't think there's any way to simplify that. Yeah, okay. All right, so just that. Yeah, so for this over here, there are no rules that we could use to simplify this. We're just gonna do it, right? So 7 to the second power, well, here's what you could do. I suppose for this one, you could say, I don't know if this is gonna make it so much easier, but you could say for this one, let me put another rule over here. If I have, let's say the bases are different, so A to some power, let's call that power C, times B to some power, let's call that power also C, then that would be the same as A times B to the C. So in this case, the exponent is what's the same. It's the bases that are different. Okay, actually we could have said the same thing for the last problem. If I have A to some exponent C divided by some other number B, but to the same exponent C, then that's the same thing as A over B, all raised to the exponent of C. This is not actually going to save us so much time, though, for evaluating this, but if we wanted to, we could say that 7 to the second power times 10 to the second power is the same thing as 7 times 10 to the second power. That's using this rule over here. And 7 times 10 is 70 to the second power, so that means 70 times 70, which is 4,900. Okay, or you could have just evaluated this without using any rule whatsoever. So if 7 to the second power times 10 to the second power, 7 squared, 7 to the second power means 7 times 7, which is 49. 10 to the second power means 10 times 10, which is 100. So we have 49 times 100, which is 4,900. Okay, I can put a comma there also. Yeah, so did using this rule save us so much time for that problem? Probably not. It's not too hard to see where this rule comes from. Actually, if we do it backwards, so starting with this, how can we figure out that this is the same as this? Because if I had started with this over here, imagine that it had not given me this, and it had given me this to begin with. Then just to figure out that this really is the same as this 7 times 10 to the second power really means 7 times 10 times another 7 times 10. But everything is getting multiplied here, And the order that we multiply things in does not matter. So oops. Okay. The order that we multiply things in does not matter. So this is the same thing as, we could say 7 times 7 times 10 times 10, because everything here is just getting multiplied. So that's the same thing as 7 times 7 times 10 times 10, which is the same thing as 7 to the second power times 10 to the second power. Okay, so starting with something that looks like this, we could figure out that it's the same thing as this, sort of just by expanding everything and writing it in different ways, step by step. All right, so anyway, this is just a 4,900. Okay, in this case, oops, that's gonna be annoying. You know what, let me pause the video for a second, and magically I'm gonna make those new rules appear. Okay, so now I have those rules over there. They have magically appeared. We talked about this one a little bit with the 7 times 10 to the second example. Let me just show you where this one comes from. So for example, if I had, let's forget about this for a second. If I had something like, I don't know, 3 over 4 to the 5th power, well, what does that mean? That means 3/4 times 3/4 times 3/4 times 3/4 times 3/4, okay? But how do we multiply fractions? We just multiply out the numerators and multiply the denominators. So in the numerator, I'm just going to get 3 times 3 times 3 times 3 times 3, which is 3 to the 5th power. And in the denominator, I'm just going to get 4 times 4 times 4 times 4 times 4, which is 4 to the 5th power. Okay, so 3 over 4 all to the 5th power is just 3 to the 5th power over 4 to the 5th power. Okay, and that's what this is saying. If we have some fraction and we're raising it to some exponent, that's the same thing as the numerator raised to that exponent over the denominator raised to that exponent. Okay? But actually, this is not the rule that we are going to use for this problem. Why not? Because here the bases are the same. We have 11 and 11. So for this problem, it would be helpful for us instead to use this rule over here, which says that if the bases are the same, like I wrote here, a and a, then we can just subtract the exponents. So this would be the same thing as 11 to the power of 7 minus 5, and 7 minus 5 is 2. So we have 11 to the second power, which means 11 times 11, which is 121. Okay. I'm going to go ahead and skip a level here. I think we had this exact problem before, didn't we? Let's jump ahead a level. Okay, so now we have some negative exponents. And it's not going to be as easy for me to explain where this rule comes from. I like to explain where the rules come from, but sometimes just in these IXL videos, I'll give you the rule and just take my word for it. This one takes a little bit longer to explain, but just take my word for it that if we have a negative exponent, that's the same thing as 1 over the same base to the opposite of that exponent. Okay, so just make it, so you would take it and make it positive. So for example, 11 to the negative second power is the same thing as 1 over 11 to the positive second power, okay? But actually we have this over 4 in this problem. So let's put both of these over 4. And then really what you could do is multiply this and this together. Let me show you why you should be multiplying those together, and then put that in the denominator. Whoops, I lost my 2. Okay, why am I going to multiply this and this? Because of keep, change, flip, right? If we're dividing here, then we could keep this the same. You guys know keep, change, flip, right? 1 over 11 to the second. So I keep this the same. I change division to multiplication, and then I flip this. So 4, if I flip it, if I take the reciprocal, 4 is like 4 over 1. And if I flip it, I would get 1 over 4. And now we're multiplying these fractions. So we multiply the numerators together. 1 times 1 is 1. and we multiply the denominators together. 11 to the second times 4, well, I'll actually multiply it out in the next step. But hopefully now you see why I said a minute ago that when you have something like this, really, all that ends up happening is that this would get multiplied by this in the denominator, okay? Because if you do keep, change, flip, then that's what happens. Okay, so now let's just do this. So we have 11 to the second power means 11 times 11, all right? 11 multiplied with itself, okay, which is 121, times 4 would be 484. So we're going to get 1 over 484. Okay, so we'll put a 1 here and a 484 over here. Okay, bleh. All right, so now over here, really what's going to happen, let me give you a quick way to do this. If you see a negative exponent, then it's like you're going to take this and bring it up to the numerator, okay, but make the exponent positive. And here again, we have a negative exponent, which was in the numerator to begin with. We're going to take this and we're going to bring it down to the denominator, but also make the exponent positive. So this is going to end up being 12 to the positive fourth power in the numerator over 12 to the positive fifth power in the denominator, okay? But let me show you why that's happening. Let me switch to pink because I like pink. So this is the same as 1 over 12 to the fifth power, right? That's according to this rule over here. And then in the denominator, we have 1 over 12 to the fourth power, okay? Again, according to this rule. But now we're just going to do keep, change, flip, okay? It looks really messy, but it's just keep, change, flip like you learned maybe in 5th grade. So we're going to keep this the same. We're going to change the division to multiplication. We're going to flip this, so take the reciprocal of it. So we would get, instead of 1 over 12 to the fourth, we would get 12 to the fourth over 1. And then multiply the numerators together. So anything times 1 is just itself, right? So 1 times 12 to the fourth is just going to be 12 to the fourth. And 12 to the fifth times 1 is just going to be 12 to the fifth. Okay? So all that work, you can see now how we got here, but now that you see how it happened, now from now on, anytime you see a negative exponent here, you could just sort of bring this down to the denominator, or if you see a negative exponent in the denominator, you can bring it up to the numerator. Okay, now actually I have to do 12 times 12 times 12 times 12. So we have 12, we have 4 12s here, 12 times 12 times 12 times 12. I'm not going to do that by hand. I will be using a calculator for that. You can as well. So let's do 12 times 12 times 12 times 12. Oh, no, they don't want us to do that. Forget, what am I saying? That's silly. I almost embarrassed myself. So the bases are the same here. So now we can go ahead and use this rule. I almost embarrassed myself so much. All right, so if the bases are the same, then we can go ahead and subtract the exponents. Okay, so we have 4 minus 5. So we're not taking the bigger number and subtracting the smaller number. We're taking the exponent that's in the numerator and we're subtracting the exponent that's in the denominator. So 4 minus 5. Okay, you have to be careful about that because 5 minus 4 is 1, but 4 minus 5 is negative 1. So over here, we're going to get 12 to the negative first power, okay, which is equal to 1 over 12 to the first power, which is just 1 over 12. Okay, 12 to the first power is just 12. Okay, so our answer here is going to be 1 over 12. All right. 7 to the negative first power is like 1 over 7 to the first power, and then we have times 7 to the third power. Okay, which we could write as 7 to the third power over 1. right? And then so we're going to get 7 to the third power over 7 to the first power. So over here, first of all, which rule am I using? I'm using this rule, and I'm writing 7 to the negative first power as 1 over 7 to the first power. And then just putting this over 1, that's something that we learn in elementary school, right? Like any number is the same, 5 is the same thing as 5 over 1, right? Okay, and then we're just Okay, and then we're just multiplying fractions. Okay, so the numerators multiplied with each other, and then the denominators multiplied with each other. And now we can go ahead and use the division rule and say that this is the same as 7 to the 3 minus 1 power. Okay, which is 7 to the second power, which is 7 times 7, which is 49. And actually, there's another way that we could have solved that problem. I could have, from the very beginning, just used this rule over here, the multiplication rule. Again, I can do that because the bases are the same. Okay, if I want to use this rule or this rule, then I have to make sure that the bases are the same. In this case, the base in both of these is a 7. So the bases are the same, so I could use this rule, and I can also use this rule. If I had used this rule, then I would have just added the exponents. Since I'm multiplying here, I can use this multiplication rule and just add the exponents. So this is the same thing as 7 to the negative first plus 3 power. And negative 1 plus 3 is also 2, just like I got over here when I used the division rule and I subtracted the exponent. Okay, negative 1 plus 3 is 2. If you forgot how to work with negatives, just think of a number line. If I start at negative 1, and then I add 3, which means I go to the right 3 places, 1, 2, 3, then I would be at positive 2. Okay, and that just means 7 times 7, which is 49. All right, over here, the exponents are different. Okay, the exponents are different, so I cannot use this rule. I can only use this rule. I'm sorry, not the exponent. Well, the exponents are also different, negative 3 and negative 2, but the bases are different, more importantly, which is why I cannot use this rule. Okay, even though I am multiplying here, I cannot use the multiplication rule because the bases have to be the same in order for me to use that rule. Here I have a 3 and an 8, so the bases are different. Okay, so, and this rule is not helpful for me either. The exponents are different, so I can't take it like this and then turn it into something that looks like this because I do not have the same exponent like C and C like I wrote over here. So we're just gonna go ahead and we can still use this rule over here. We have some negative exponents, so we can rewrite 3 to the negative third power as 1 over 3 to the third power, and we can rewrite 8 to the negative second power as 1 over 8 to the second power, and then we're multiplying these things together. Okay, so 1 times 1 is 1. And then 3 to the third times 8 to the second. So 3 times 3 is 9, and then times another. So 3 to the third means 3 times 3 times 3, right? So 3 times 3 is 9, times another 3 is 27. So I have 27 times 8 to the second power means 8 times 8, which is 64. So I have 1 over 27 times 64, and then let's just use a simple calculator for that. So 27 times 64 is 1,728. Okay. Oh, we finally get to use the 0 power, or the 0 rule. I don't think we've used that this entire video. Okay, so anything to the power of 0 is just 1. Okay, you're just gonna have to take my word for it right now. In this video, I'm not explaining where that rule comes from. Just take my word for it. Okay, so we're using this rule. 12 to the second just means 12 times 12. Okay, and then we have times, right? The dot also means multiplication. So times 2 to the 0th power, which is just 1. Anything to the 0th power is just 1. Okay, that's something that that's a rule that mathematicians have invented. They invented it for a good reason, that anything to the 0th power should be 1. But it is something which is invented. I'm not going to get into why it was invented that way in this video. Just take my word for it that there's a good reason why people have defined it to be that way. But anyway, right now, let's just use the rule and say that this whole thing is just 12 times 12 times 1. 12 times 12 is 144, times 1 is still 144. Okay, so we're going to get 144 here. All right, let's try for this one. You know what? Let's go ahead for this one. There are a couple ways we could do this. We could use the negative rule, which we've used a few times already. And I could say that this 2 to the negative second power is the same thing as 1 over 2 to the positive second. And 2 to the negative fourth is the same thing as 1 over 2 to the positive fourth. But you know what? We also have another option here. Since all of these have the same base, the base is 2 for all of them, they're all getting multiplied together, we can go ahead and use the multiplication rule, and we can add the exponents. Okay, so this is the rule that I'm going to choose to use now. So that's just going to be 2 to the negative 2 plus 4 plus negative 4. Okay, I'm just adding all of these exponents over here. Okay, don't forget that when you add a negative number, that's the same thing as subtracting positive, right? So adding negative 4 is the same thing as subtracting 4. So now let me rewrite this as 2 to the negative second plus 4 minus 4. Okay, I'm still using this rule, but I'm also remembering that adding a negative is the same thing as subtracting a positive. And let's evaluate all this by using a number line. Okay, so if we start at negative 2, and then we go to the right 4 spaces, 1, 2, 3, 4, then we would be at positive 2. But then we're going to go to the left 4 spaces. So now from here, I go to the left 4 spaces, and now I'm back where I started, at negative 2, right? So this is going to be equal to 2 to the power of negative 2. And now I can go ahead and use this rule and say that this is equal to 1 over 2 to the positive 2, which is just 1 over 2 to the positive 2 means 2 times 2, which is 4. So 1 over 4. Okay, I think I'll do this, and then I think I'm going to jump a level. Let's see, we can simplify a little bit here because these bases are the same. We have a 4 here and a 4 here. So let me just keep the 12 to the second and then times. For this one, I'm going to use the multiplication rule that we used before. Okay, which tells me that I can just add the exponents. So this is times 4 to the negative 6 plus 7th power. So negative 6 plus 7 is positive 1. If you think of a number line, if you're at negative 6, if you go 7 spaces to the right, then you would be at positive 1. Okay, so we're going to get 12 to the second times 4 to the positive 1. So this is just 12 times 12 times 4. Okay, so we have 12 times 12 is 144, and then 144 times 4, let's just work that out over here. That's going to be 4 times 4 is 16, plus 1 is 17. Okay, that's going to give me 576. Okay. For this one, you know what? Very quickly, I'm going to do that little trick that I told you about earlier. I could use this rule and then do keep, change, flip. But I already did that earlier in the video. Hopefully you've watched the entire video up to this point. And if you have, then you saw that in the end, what's going to happen is we're going to get 11 to the second power in the numerator, and we're going to get 10 to the first power in the denominator. Okay, so 11 times 11 is 121, and 10 to the first power is just 10. All right, let's go ahead. Here, all the bases are the same. You could just use the multiplication rule and just add all of these up. 9 plus -6, which is like 9 minus 6. And then plus -2, which is like -2. So 9 minus 6 is 3. And then plus -2, which is like -2. So 3 minus 2 is 1. So we're going to get just 8 to the first power, which is 8. That one actually wasn't too hard. But you know what? I'm going to go ahead now and jump ahead. Let me see if I get anything significantly different. If not, I'm just going to end the video here. Okay. All right. So 4 is like 4 to the first power. So I could use the multiplication rule, and I can add the exponents over here because the bases are the same. So I'm allowed to use this rule and the division rule when the bases are the same. Okay, so that's going to give me 4 to the 7th in the numerator and 4 to the 4th in the denominator. I just kept that the same. Okay, then I can use the division rule and subtract the exponent. So this is going to be 4 to the 7 minus 4th power, which is 4 to the 3rd power, which means 4 times 4 times 4. 4 times 4 is 16, times 4 is 64. Okay. All right. Actually, over here, to make it a little bit easier, you could use that rule that I said before. If I see 5 to the -2nd power here in the numerator, I can bring that down to the denominator and just make that -2 a +2. But then I see another 5 to the -2 in the denominator. I can bring that up to the numerator and again just make the -2 a +2. And then I still have this 5 to the 3rd in the denominator. So that's going to give me 5 to the 2nd times 5 to the 3rd using the multiplication rule and adding the exponents. I would get 5 to the 5th. And then I can go ahead and use the division rule, again, because my bases are the same. The bases are both 5 here. So then I can use the division rule and subtract the exponents. So 2 minus 5, careful, it's 2 minus 5, not 5 minus 2. 2 minus 5 is -3. So I'm going to get 5 to the -3rd power, which is 1 over 5 to the 3rd power using the negative rule. And then that's just, so in the denominator we have 5 times 5 times 5, right? That's what 5 to the 3rd power means. 5 times 5 is 25 times another 5 is 125. So we're going to get 1 over 125. Okay. Let's do one more, and then I think I'm going to end the video there. Okay, I'm going to use that little trick. If I have a fraction here and I have something with a negative exponent, then we can use that little trick. And if it was in the denominator, we'll bring it up to the numerator and just make the negative exponent positive. If it was in the numerator, we'll bring it down to the denominator and still make the exponent positive. All right, so I'm going to bring this up to the numerator. So I already had a 2 to the 2nd power in the numerator. Now I'm going to have another 2 to the 2nd power. Okay, and then in the denominator, I'm just going to have 2 to the 3rd power now. Okay, this is going to be the same as 2 to the 4th power. 2 to the 2nd times 2 to the 2nd is 2 to the 4th, using the multiplication rule. Since these are getting multiplied and the bases are the same, I can add the exponents. So 2 plus 2 is 4, over 2 to the 3rd. Now, again, the bases are the same, so I can use the division rule and I can subtract the exponent. So 4 minus 3 is 1. So I get 2 to the 1st power, which is just 2. Okay, unless the next problem is something that's really, really different, I think I'm just going to end the video there. Okay, it's complicated, but you could figure it out, again, using everything that you've learned in this video. So I'm going to go ahead and end the video there, and have a great day.